Hello, this is Jack Jackson. In this section of notes on discrete probability, we're going to talk about some Bayesian techniques, and named after a mathematician, statistician named Bayes, who came up with some of these ideas and made use of them. And basically what we're going to do is we're going to be leveraging the interplay between two different trees. So we're going to start with an introductory example that has two probability trees. Okay, so let's just review first of all some properties of probability trees before we go any further. We should be pretty good at these probability tree properties by now if we've worked through the other videos in this this playlist that came before this, or the material that goes along with it. So probability trees start from a root vertex, and each column of vertices represent all possible events for that stage. All events coming from a particular vertex must represent all the non-overlapping events at that particular point. And the edges, the line segments are called edges, they are labeled with probabilities. All the probabilities emanating from each vertex must sum to 1. And after the first level, all probabilities are actually conditional probabilities, and they're probabilities given that all the events earlier in that path that led to that point have occurred. So, by the definition of conditional probability, we can multiply all the probabilities along each path to find the probability of the intersection of events along the path. We write these probabilities at the end of the path, end of each path. So the intersection of probabilities is at the end, therefore disjoint events, and so they can be added up, and they all, if you add all of them up, they must add up to 1. So this and maybe one other property are the main properties we need to know about probability trees. Now, remember, the definition of conditional probability is that the probability of A given B is defined to be the probability of A intersect B divided by the probability of B. If we multiply both sides of that equation by the probability of B, we solve for the probability of A intersect B to be the probability of B times the probability of A given B. But we can similarly say that the probability of A intersect B is the probability of A times the probability of B given A. Now, since this probability of this intersection is the same probability, either way we write it, we now know that the probability of B times the probability of A given B is the same as the probability of A times the probability of B given A. So there are two ways of computing this intersection, this way and this way. And these two ways then give us a connection between two different probability trees, because one tree will have the probability of B and the probability of A given B in it, and the other tree will have the probability of A and the probability of B given A in it. And this key fact is going to allow us to connect the two trees together, and this is going to be the thing that allows us to work through the techniques in this section. This is the key observation, and we're going to leverage this for some good results. So let's look at our example here. Suppose that the probability that contestants in a statistics competition are assigned to exactly one of two judging panels. Let me rephrase that. Suppose that contestants in a statistics competition are assigned to exactly one of two judging panels. And the probability that a contestant is assigned to, say, panel A is 70%. Furthermore, let's say we know that 65% of the contestants that were awarded an outstanding rating were judged by panel A. And we furthermore know that 20% of all the contestants earned an outstanding rating. So just to give us some letters here, let A be the event that a contestant was judged by panel A. Let O be the event that a contestant earns an outstanding rating. So what if we can do, the first thing we might want to do is represent the three probabilities that we have up above symbolically, and let's switch them to decimal form. So let's start with that. Go ahead and do that, and then when you're ready, continue on. Well, their assigned to panel A is just probability of A, which was 0.7, 70%. And this is that 20% of all of them earned an outstanding rating, so the probability that a contestant earned an outstanding rating is 0.2. Now be careful on this one. This says 65% of the contestants that were awarded an outstanding rating were judged by panel A. So we know they were awarded by an outstanding rating, so that's going to be a probability given O. So this is the probability of A given O. Be sure you kind of keep that straight between probability of A given O, the probability of O given A, the probability of A and O, probability of A and or O. Keep kind of those things kind of straight in your mind there. Okay, so this one is a conditional probability. Now, the main thing that we're interested in finding out actually is the probability of O given A. We want to flip it around. So we know the probability of A is 0.7. We know the probability of A given O is 0.65. We know the probability of O is 0.2. The main thing we're interested in finding out is what is the probability of O given A. So we have basically probability of A given O. We want to flip it around backwards. And we know from our previous examples this is not necessarily the same thing. In fact, it could be very different than either probability of O or the probability of A given O. Now it may look like we don't have a lot of information here, but it turns out with what we know about probability trees, just these three pieces of information are enough for us to fill out all kinds of information about this situation. Okay, now see if we can put those probabilities in these trees. Okay, so there's the tree. You might want to jot these down first. This one, notice it has O and not O first, then A and not A second. This one has A and not A first, then O and not O second. So see if you can take the probabilities that we have and put them in the appropriate places in these trees. Now let me back you up here and remind you that these are the probabilities that we're dealing with. So jot these down if you don't have them. Probability of A is 0.7. Write that down. Probability of A given O is 0.65, and probability of O is 0.2. Write those three numbers down and what they represent. And then, you got them? Okay. Now take that and go to this tree and put them in where they go. When you have that done, come back. Press pause now. So what you should have is right here. So the probability of O is right here. That's 0.2. Probability of A is on the other tree. It's 0.7. Notice this probability of O is in the left tree, but it's not in the right tree. And probability of A is in the right tree, but it's not in the left tree. And then the other probability we have, the conditional probability of A given O is 0.65, is on this edge right here. The one we're really mainly wanting to look for is actually the probability of O given A. It'll be the label on this vertex or this edge right here. But actually, we've got enough information, believe it or not, to completely fill out both of these trees. You know how to do this. Just use your skills about filling out trees. So there's one skill we know about probabilities coming out of a vertex. Use it to fill out what you can right now in these trees for the next step. Press pause and come back when you're ready. Well, did you use it to figure out this vertex or this edge right here? Well, if the probability of O is 0.2, these two add up to 1. There's only two of them, so this must be 1 minus that one. So 1 minus 0.2 is 0.8 for that one. Similarly, these two add up to 1 coming out of O here. And so this one is 0.65. The other one has to be 1 minus 0.65, so it's 0.35. And likewise, if we know probability of A is 0.7, we know probability of not A is 1 minus that's not typed in right. That's 1 minus 0.7, but it is 0.3. That's correct. Okay. Now what else can we complete? We've got all the probabilities along that path. Does that give you something else that you can complete? Well, remember that the probability of A given B is probability of A intersect B divided by probability of B. So the probability of the intersection, once again, of A and B is probability of B times probability of A given B. And the probability of the intersection is also probability of A times the probability of B given A. Use that information to go back and get the probabilities at the ends of the paths here and here. Press pause. Okay, now you're back. Hopefully you've done that. So what do? We take the 0.2 times the 0.65, that is the probability of O times the probability of A given O, and that gives you the probability of O and A, or O intersect A. And of course 0.2 times 0.65 is 0.13. Similarly, we take the 0.2 times the 0.35 to get 0.07 for the probability of O and not A. Okay, so let's put this in context again. This is the probability that they were judged outstanding, ranked outstanding. That's a 0.2. The probability that they're outstanding, given that they were judged by panel A, is 0.65. The probability that they're both outstanding and judged by panel A is 0.13. The probability that they're outstanding, given that they're judged not by panel A, by some other panel, is 0.35. And the probability that they're outstanding and judged by another panel is 0.07. Now, does anything that we have here tell us anything about the tree over here? If so, fill that out in the second tree. Press pause. Well, the thing to notice is if you multiply along this path, you get the probability that both O and A happen. Well, if you multiply the probabilities along this path here along the top, you get the probability that both A and O happen. Well, it doesn't matter which one you say first. The intersection of A and O is the same as the intersection of O and A. So this probability of this path right here is the same as this one right here. And similarly, you can find this one over here as well. Here it is. If you take this probability of this path, that's O and A, that goes right here. This one's O and not A, so it's down here too. So these four probabilities that go at the end here actually turn out to be the same as the four probabilities at the end here, although they might be in a different order. All right? Now let's focus on the second tree a minute. We have the two probabilities of these two edges, and we have these two at the end. Can we figure out something else in this tree? Specifically, how about this edge and that one? See if you can do that now. Press pause. Now, whatever this is, hopefully you're back now with the right answer, but hopefully whatever it is, you realize that if you multiply the probability here times the probability here, you get the probability at the end. Well, we have the one at the end and one here. We're missing one of the factors along the way. The opposite or inverse of multiplication is division. So we just take the 0.13 divided by 0.7 to get the value here. And similarly, we take the 0.07 divided by 0.3 to get the value right there. And here you see it worked out. At least rounded off to 2 decimal places. These are the correct answers. So here we have, again, the 0.13 divided by the 0.7. And that gives us 0.19. And here we have the 0.07 divided by the 0.7 is 0.23. Okay. Well, can you finish the second tree? What's the next step? Do it now. Well, remember these add up to 1. So if the green one here is 0.19 for this top edge right here, then this one other one that comes out of it must be 1 minus 0.19, which is 0.81. And similarly, if we know this one right here, which is the green one, 0.23, the other one that's coming out of the same vertex here, that's the only other possibility, these have to add up to 1. So the one down here I've got in purple over here is 1 minus the 0.23 or 0.77. So we have all the edges labeled in the second tree. The only thing we're missing in the second tree is this value right here at the end of this path where it goes A and then not O. And then we're missing the one at this end that's not A and then not O. So fill out those last two. Press pause. Well, we fill those out by just multiplying, remember? So we use the multiplication rule. So this is 0.7 here times the 0.81 here gives us 0.57. Okay, at least these are rounded off to 2 decimal places. But then here you get 0.7 times the 0.77. Multiply those together and you get 0.23. So the second tree's done. We're almost done now. Can we go back and put is any of this information helpful in the first tree? Well, yeah. The two red probabilities here are O and A, and O and not A. They showed up over here, O and A and O and not A. Similarly, not O and A shows up at the end of one of these paths, and this one here shows up here. Put them in the right places. There they are, right there. So the two orange numbers we just copied over. So again, the big connection here that makes this work is that these four numbers here at the ends of the paths, the intersection probabilities or joint probabilities, are the same as the four numbers at the ends of the paths here. They're the same joint probabilities. Now, remember, let's see what else. We only got a couple things left to do. It's these two edges. Go ahead and fill them out. And remember, we do that by what? Dividing. 0.57 divided by 0.8 goes here. 0.23 divided by 0.8 goes here. And of course, we should be able to check it because these two should add up to 1. So you could check all the pieces now of the trees. If you add these two up, it's 1. If you add these two up, it's 1. Add these two, it's 1. Add these two, it's 1. Add these two, it's 1. Add these two probabilities, it's 1 here. Multiply along the paths. Multiply this times this to get this one times this one to get here. This one times this one here to get this one. And this one here times this to get here. And similarly on this side, and then the probabilities, the four probabilities at the end are the same. So here's the same thing with just the probabilities written down and what they're the probability of without showing you how the computations are done. Just kind of clean it up a little bit in terms of presentation here. So these are all the probabilities that we have. So far, we'll just read them off real fast. The probability of O, a probability of outstanding rating is 0.2. Probability not outstanding, 0.8. The probability of an outstanding, of being judged by panel A given its outstanding is 0.65. And the probability of not being judged by panel A given its outstanding is 0.35. The probability of being judged by panel A given you didn't get an outstanding is 0.71. And the probability of not being judged by A given a not outstanding is 0.29. The probability that the contestant was judged by panel A and given an outstanding rating was 0.13. So there's 13% of the contestants fell in that category. 7% of the contestants were both outstanding and judged by some panel besides A. 0.57 is the probability of not outstanding and judged by panel A. 0.23 is the probability of not outstanding and not judged by panel A. Those are all in the first tree. In the second tree, we have the probability of A is 0.7. The probability of not A is 0.3. Probability of outstanding given A is 0.19. So probability of outstanding, not outstanding given A. Probability of not outstanding given A is 0.81. Probability of outstanding given not A is 0.23. Probability of not outstanding given not A is 0.77. And again, these are the same probabilities here at the end that we had over here in the other tree in a different order. So we've been able to figure out everything. I mean, every probability that you want basically is in there somewhere. We've got the intersection probabilities, the joint probabilities. We've got the conditional probabilities. Let's see, so there's 4 joint probabilities. They show up in both trees. We have the 8 conditional probabilities there, and we have the 4 just regular probabilities. And all of that shows up in the tree. So if you understand how trees work, this works together. And the one we were mainly interested in was the probability of outstanding, given that it was judged by panel A, was 0.19. And notice that could be very different than the probability of A given outstanding or the probability just of outstanding, they might be very different. If they were independent events, this would be the same as the probability of outstanding. And see, they're close, but they're not quite the same here. Now, we can record a lot of this information in a contingency table, two-way contingency table, or sometimes called a cross-tabulation table. We can put this information. So we're going to put some of these same numbers in here, and the four numbers right here, the 13%, 7%, 57, and 23, let's look back. Those are the numbers that right here, 13, 7, 57, and 23%. Those are the joint probabilities, or the intersection probabilities. They're right here. 13% were both A and judged by panel A and outstanding rating. Outstanding rating and not A was 7%. Okay, the row sum here, 13% plus 7% is 20%. Let's see where that comes into play. Well, that says this 13% plus that 7% is that 20% there. See how that works? So these are the only ones that are outstanding. These are not outstanding here. So these are the only two possibilities. We split up the outstanding into the outstanding and A and outstanding and not A. But together these are all disjoint. So these probabilities at the end can be added. In fact, they all add up to 1, of course. And so if you add those two together, you get the 0.2. Similarly, we add the 0.57 and the 0.23 to get the 0.8. And those are actually then, let's see, those are actually the row sums here, right? Probability outstanding, probability not outstanding. The column sums are the probability of A and not A. Those are the marginal probabilities. All four of those are called marginal probabilities. So the marginal probabilities are the ones here, right? The first ones. Probability O, not O, probability A, and not A. And we can see that over here. If we add the 0.13 and the 0.57, we get 0.7. And if we add the 0.07 and the 0.23, we get 0.3. And that shows up there, and that shows up as a column sum here. Of course, if you add everything up, you get 100%. And so we have a lot of the same information, not everything, but a lot of the same information given here in this two-way contingency table. What's here and what's not here? Well, if you notice, the four probabilities right here are the same as the four probabilities here. These two and these two, the two first ones in each tree, and those are the what we call marginal probabilities. And the ones at the ends, these four and these, which are the same as these four, are the four probabilities right here in the middle. What's missing, however, are these other 8 probabilities, these four and these four right here, which are the 8 conditional probabilities. That doesn't show up in the table here. Now we could figure them out from here, of course. For example, we know how to do that. We would take probability of outstanding given A would be 13% divided by 70%. The 0.13 divided by the 0.7. We see that here is the 0.13 divided by the 0.7 is the 0.19. That's how we figured out the 0.19, if you remember. And so forth. We could also represent these four values here in a Venn diagram. And so remember what they are and look at the colors. 13%'s got the black background, 7% here, and so forth. And here's the same things with the same colors. Whoops, back here. Here. So by A is here. This is A. A is these two put together. So this yellow part here is A and not outstanding. This is A and outstanding. This is outstanding and not A. And the other 20% is neither A nor outstanding. And those are the four pieces there. And so those are just the joint probabilities. Actually, less information in this diagram than in this one because it just has these four. And there's really less information here than there is in the table because this has the conditional probabilities as well. Okay, so here I've got another exercise for you. It works very similar to the last one. Okay, in fact, it's extremely similar. It's just changing the numbers. So, but I want you to practice a little bit. So suppose the probability that contestants in a statistics competition are assigned to exactly one of two judging panels. The probability that a contestant is assigned to panel A is 40%. 80% of the contestants were awarded an outstanding rating. 80% of the contestants that were awarded an outstanding rating were judged by panel A. And 10% of all contestants earned an outstanding rating. Again, use the same letters as before, and what I'd like you to do is complete the dual tree diagrams, the two-way contingency table, and the Venn diagram, just like we did in the last example, showing all the relevant probabilities. And this may take you a minute or two, so we're going to ask you to press pause, work it all out, and when you come back, we'll give you a solution that you can check against what you've done. It's very important that you work through some of these exercises yourself as you're going through these videos and not just watch me do them. But of course, because you really learn it when you do it yourself. So press pause now. Well, I'm not going to go through all the steps. They're the same as last time, but you can check your work against here. So you may want to pause this and make sure you got all the same numbers as we have here. And the steps are exactly the same, just like last time you were given the probability of O, the probability of A given O, and the probability of A. So it's exactly like the previous example in terms of the steps, and this should be your final result here. Here is the two-way contingency table, and then here is the Venn diagram. Okay, we're going to use these ideas some more with some more exercises in the next video, but let's go ahead and stop this video for now.